Hi folks, Mr. Long here. This is going to be part 2 of the screencast on rough sketching composite functions slash radical functions. Okay, so let's get going here. Oh, I seem to have misplaced my pen. Just 1 second here, folks. Okay, here we go. So this is number 11 on the sheet, and I'll go through it. It looks very similar than the last one that we did, but it's still worth going through. So again, what we want to do is look. First thing we should do is domain. Okay, domain for the original function, and again, we look at each factor separately when we do this in a product. So I look at x. Well, what's the domain for y equals x? Well, it's everything. You can sub any number into there. But what about this x plus 8? Okay, what about x plus 8? What has to be true about x plus 8? X plus 8 always has to be greater than or equal to 0. Okay, and if we subtract 8 on both sides, what we end up with is this right here. X must be greater than or equal to negative 8. Okay, so that's our domain then, because I can't have negative 9 in there. Even though negative 9 is fine for this x, it's not fine for the x under the root sign. Okay, so the domain for this graph is x is greater than or equal to negative 8. So there's nothing to the left of negative 8 in this graph. Okay, so I've done my domain. Next thing I want to do is the end behavior. And you know, I think, again, we can go through this. So what's the leading term going to be? The leading term for this one, what will it be? Well, it's going to be x multiplied by root x. So it's going to be x to the, again, 1.5, which is, in fact, 3 over 2. Now, with regards to end behavior, so I know it's x to the 1.5. Do I need any end behavior for far to the left? No, because x has to be greater than or equal to negative 8. I don't have to deal with far to the left. Far to the right, however, if I put a number in far to the right, like 1,000, a million, a billion, and I raise it to the 1.5, what's that going to give me? Yet another positive. Okay, so I know that the graph ends up high to the right. What about x-intercepts? Okay, so x-intercepts, I'm going to change the x plus 8 instead of square root. I'll put it to the 1/2. And so for this one here, for the x, well, if I set that equal to 0, I get 0. If I set x plus 8 equal to 0, I get negative 8 as x, so that's negative 8. What kind of x-intercepts are there? Well, the first one here, that one is linear, so it's a single x-intercept. And then what about the x plus 8, the negative 8? Well, the exponent outside that is 1/2. 1/2 is square root. That's a one-sided cusp. Okay, a one-sided cusp. So again, I go over to my graph, and I know I've got something at negative 8, well, one-sided cusp, and then a linear x-intercept at 0. So if it's a one-sided cusp, let me think about this. So in this case, sometimes it makes more sense to go from the right than the left, because I know that the graph doesn't exist out here, right? There is no graph. It's only to the right. I'll put an arrow across. It only goes to the right of and including negative 8. But here, I know it goes like this, and then it has to go through 0. And then what kind of an x-intercept is it at 0? It's a single, so it crosses through. And then what it has to do is come around and finish up there in a one-sided cusp. So again, what we know is that a one-sided cusp is vertical at the start, okay, and then it goes like this. So it looks something like that, right? A single x-intercept at x equals 0. And then a one-sided cusp at x equals negative 8. So that's what your graph looks like. So you know you've got a minimum somewhere down here, and it's probably going to be closer to negative 8 than it is to 0. Okay, folks, so that's your rough sketch there. There's a lot of good thinking in this. All right, so here's another one. This one here. Cube root of x multiplied by 10 minus 2x. This one is very similar to both, or all of 12, 13, and 14. And this one is already in factored form, which is kind of nice. And so let's take a look at that. Start with our domain, like we have every other time. Okay, we're going to start with our domain. So the first factor was the cube root of x. Again, the questions I need to ask are, can I have negatives? Can I have 0? Can I have positives? Well, if I look at that, cube root, can I take the cube root of a negative? Yeah, for sure I can. Yeah, and 0, yeah, and positives, yeah. So anything at all. Okay, so in that cube root factor, I can have anything at all. What about this factor here, 10 minus 2x? Because again, remember the function is y equals cube root of x multiplied by 10 minus 2x. What about 10 minus 2x? That's just a linear function. I can have any x value at all there. So what's the overall domain? X belongs to the real numbers. I can have any x value I want for this function. Now let's get our x-intercepts. So for the first factor, cube root of x, set that equal to 0, I get 0. And that's a cube root. So that is a odd over odd. That's an odd, whoops, that's an odd root. Okay, I'll need to lift that up a bit there. So that's an odd root. Okay, an odd root. And then we go to the other one, 10 minus 2x equals 0, the linear factor, which is a single. If I solve that equation, I get x equals 5. And that's, again, a single. Okay, so I've got an odd root, and I've got a single root, so or x-intercept. So remember that the odd roots look like the cube root graph, so they're like this, right? They go vertical there for an instant, and then I've got a linear. So this x equals 5, so it crosses the x-axis, and even though it may be curved on either side, when it crosses through, it's approximately linear. Okay, so now let's do the end behavior. And notice I could have done, the order that you do end behavior and x-intercepts really doesn't matter. So what is our leading term here? This one's a little trickier to do your leading term. Let's take a look at it. So again, greatest exponent in what we would call standard form. So I could, it's going to be cube root of x times by negative 2x. That's going to be the leading term. Okay, cube root of x times by negative 2x. That's the leading term. So what is it? It's x to the 1/3 multiplied by negative 2x to the 1. What do we do when we multiply? We add exponents. 1/3 plus 1 or 1/3 plus 3/3. That's 4/3. Okay, so our leading term is negative 2x to the 4/3. Okay, remember the leading term is the term with the greatest exponent in standard form, so when it's all expanded out. So negative 2x to the 4/3. So if I think about this, okay, so if I think about this 4/3 here, I've got an exponent of 4/3. The 3 is cube root, the 4 is repeated multiplication. Well, if I've got an exponent of 4 there, okay, an exponent of 4, even if x is a negative, if I multiply something 4 times in a row, I'm going to get a positive. So in this graph, this is an interesting graph from an end behavior perspective because I've got a negative multiplied by something that's always positive, right? So the negative 2 is always negative. Then that multiplies by what's always a positive, because it doesn't matter what goes in for x, it's going to be to the 4th, right? It's going to be cube root, which can be negative, but then I raise it to the exponent of 4, it'll be positive. So it's a negative times a positive, which is a negative. Far to the right, same thing. That negative 2 is still there in the equation. And then anything to the far right is going to be positive for x. So it looks as though I point down and I point down. Okay, so let's look at this graph now. So I had a single x-intercept at x equals 5, and I have a cubic, or third root, not a cubic, but a third, like an odd root at x equals 0. My end behavior is negative and negative. Okay, it's pointing down far to the left and far to the right. So here's what I know then. I know that a cube root passes through like so. Okay, it's a vertical tangent with the 1/3 there. So it's gonna do this. It's gonna pass through like that, right, and point down. And then this is going to go like so and come down like so there and go down. Okay, there's your rough sketch. Okay, just again, you have to know the shape of the x-intercept, and you have to know where the x-intercept is, and you have to know the end behavior. Once you do that, it's fairly easy to sketch. And you're also going to know things like when you go to do absolute max and min in an interval, you're going to know that you're going to have to get a maximum probably between 0 and 2, I would say. X equals 0 and x equals 2. Because if you don't, then you know you've made a mistake. Okay, just 2 more sketches to go through. This one is probably the toughest one on here. And if you don't, I wouldn't, for me, well, I wouldn't ever test this type of question. It's pretty difficult. On the other hand, it's probably something that you can do. So it's number 15 on the list, and there is one more like it, so you get some extra practice here. So y equals negative x times by 1 minus x squared. Again, one of the things we always want to do, if we can, is to factor, right? We want to be able to factor. So the thing that I see on here that's factorable is 1 minus x squared. That's a difference of squares, 1 squared minus x squared. So it's 1 minus x, 1 plus x. So if I rewrite this, I can rewrite it with 1 minus x, 1 plus x, all under the root sign. But what exponent is that? Well, it's 1/2. So I rewrite it this way. Negative x multiplied by 1 minus x to the 1/2, 1 plus x to the 1/2. Okay, and I do that, I rewrite that first. And now let's go and let's look at our domain. This is where things get, this one is tough for domain. Again, I encourage you to pause, rewind, and you could fill in examples if you want, copy these down. I'm going to put hard copies, I think, of these in as well in the notes, or rather on the Google Classroom post. Okay, so what do we know here? So the original equation was y equals negative x square root 1 minus x squared. So what do I know? I know that this right here, 1 minus x squared, has got to be greater than or equal to 0. I know that. So I can factor that. I know that 1 minus x multiplied by 1 plus x has to be greater than or equal to 0. Now I can do what's called a test table, but I'm pretty sure you know how to graph 1 minus x, 1 plus x, right? The x-intercepts are 1 and negative 1 from the two factors. I know it's negative x squared, so it's a frowning parabola. There's your graph right there. And it says, again, this 1 minus x squared has to be greater than or equal to 0. So it has to be this area here that I've highlighted. So the only values where 1 minus x squared is greater than or equal to 0 is when it's in between negative 1 and 1. I'm not allowed to have any of these values out here. I'm not allowed to, because they generate negatives. And I can't have a negative under that square root sign. Okay, so the domain for this graph is just between negative 1 and 1. Okay, negative 1 and 1. That's the entire domain of this graph, negative 1 and 1. I'm not allowed to go further to the left than negative 1. I'm not allowed to go further to the right than negative 1. So let's look at our end behavior. Think about that for a second. The graph only exists between 1 and negative 1. There is no end behavior on this graph. There is no end behavior. Okay, so now let's look at the x-intercepts then. So for this one in the x-intercepts, again, there's 3 factors. One factor is the negative x. Another factor is 1 minus x. Another factor is 1 plus x. What I can do then is apply that, because that square root is exponent of 1/2, and I can put them on each factor. So that negative x, that's a single x-intercept, linear. Then it's 1 minus x to the 1/2, and it's 1 plus x to the 1/2. Well, what does that work out to then? I've got 3 x-intercepts of 0, 1, and negative 1. The first one, x equals 0, is a single. Then the other one is a one-sided cusp. Both of the other ones are one-sided cusps because of that exponent of 1/2. Okay, so this is where things get interesting. How do I graph this? And I remember the first time I did a question like this. It's funny, I always remember the things that I struggled with in math. And I remember that, now this one, I think I had to sketch something like this in university, not even in high school. But I remember that I struggled with knowing, should the graph go, because I know it goes through the one, oh, I should probably have a pen here. So I know that the graph, so does it do this, right? Or does it do this, right? Which one of those is it? And I remember that that's something I struggled with. Well, what you have to do is you have to look at the equation. Y equals negative x multiplied by 1 minus x to the 1/2, 1 plus x to the 1/2. What do we know about these two factors because the exponent 1/2? That those values always have to be positive or 0. So the only thing that can cause a change in the sign from negative y values to positive y values is the negative x. So if I think about that, if I'm in between -1 and 0, that means that this x is negative. What's a negative multiplied by a negative? That's a positive. So that means that the graph between -1 and 0, the graph is positive. Now what about when the graph is between 0 and 1? Well, that number is positive. The negative of a positive is a negative. And again, so you'd have a negative multiplied by this. This has to be positive. So the graph is then a negative here. Okay, so now we know the shape of the graph. It should be fairly easy to sketch. Here's what I know. I know that at -1, it's a one-sided cusp. So it's vertical like so. Then it goes up, and then it comes down. It's a single through there, comes down here, and then it comes back up there. And it's a single cusp there. So the parts that are vertical looking are right there and right there. Okay, and that's it. That's your entire graph. It does not exist to the left of -1 and to the right of 1 because of that square root. Okay, last one finally. So this one here is like number 1, number 2, number 3, and number 4. These ones are tougher. I shouldn't have had them as 1, 2, 3, and 4 because these ones you're going to have to actually factor. So we're going to do, well, this one is number 5. So here it is, 2x minus 6x to the 2/3 plus 5. Well, here's the way we're going to graph it. We're just going to pretend that this plus 5 isn't there. And then at the very, very end, we're just going to shift the graph up by 5, okay, when we get done. Because again, we're just drawing a rough graph. We want to know the shape, the general shape of the graph so we can test whether or not our answers for the calculus part are reasonable. Plus 5. Okay, so here we go. I'm going to pretend that the plus 5 is not there. So what I'm doing is I'm going to common factor 2x minus 6x to the 2/3. So one of the things that I'm going to do is I'm going to write 3/3 there. Okay, and when I common factor, I'm just common factoring this part, I remove the greatest common factor. Well, it's always the lowest exponent. So I'm factoring out x to the 2/3, but I also have to factor out a 2 because 2 and 6 have a common factor of 2. So I'm factoring out the 2/3, x to the 2/3. What does factoring mean? It means division, right? Factoring means division. What do I do when I do division? I subtract exponents. So if I look at this one, 3/3 divided by 2/3 means 3/3 minus 2/3 for the exponent, which is 1/3. Okay. Then I'm factoring out -6 divided by 2. Well, that's just -3. And I've got x to the 2/3 divided by x to 2/3, which is 1. Okay, so it's just minus 3. So let's go over here then. So once I've got it factored, y equals 2x to the 2 over 3 multiplied by x to the 1 over 3 minus 3. All right, so let's look at, again, domain and range. Sorry, not range, we're going to look at domain. So I look at this part. You always look at the factors separately. Can I have negatives in x to the 2/3? Well, it means cube root and then square. Can I cube root a negative and then square it? Sure I can. Yeah, so I can have negatives and positives. So that's anything. X belongs to the real numbers. And then what about this? What kind of numbers can I cube root? Can I cube root 0? Yeah. Can I cube root, because 1/3 is cube root. Can I cube root a negative? Yeah. And I can cube root 0 and positives. So that's x belongs to real. So the overall domain for this equation is x belongs to the real numbers. Okay, x belongs to the real numbers. Now I have to determine the x-intercepts by setting each factor equal to 0. 2x to the 2/3 equals 0 means that x equals 0. What kind of an x-intercept is that? A two-sided cusp because of the 2/3. Then I do this one, x to the 1/3 minus 3 equals 0. Remember that that's your entire factor there. There is no exponent outside that factor. This is where a common mistake is made, where people think it's an odd root. Okay, it's an odd root, so it looks like x cubed, but it's not. It's x to the 1/3 minus 3 equals 0, right? X to the 1/3 minus 3 equals 0. So if we think about that, and there is a way to analyze this to understand that the x-intercept is not a 1/3 root. So let's take a graph, and what if I just graphed this? Well, really what it is x to the 1/3 shifted down by 3. So the graph would be like this, right? It would come along like so, and then right here at -3 it would go horizontal, and then it would go up like that. Okay, so when it crosses here, whoops, when it crosses right here, it's a single. Okay, it is in fact a single x-intercept. Okay, so I then finish solving that. X to the 1/3 equals 3. How do I undo 1/3? Well, I multiply that exponent by 3, and then I have to put an exponent of 3 on here as well. That gives me 27. So I have x equals 27 is a single. I have x equals 0 is a two-sided cusp. Okay, what will that graph now look like? Let's take a look at this. Oh, I didn't do the end behavior, did I? So what is the end behavior? This one was pretty easy. The greatest exponent in the start was 2x. So far to the left, it's going to be 2 times by negative infinity. That's a big negative number. Far to the right, 2 multiplied by a big positive gives you a positive. So far to the left, we're down low. Far to the right, we're up high. So when I go to do this, when I go to sketch this, I know that at 0, it was a double, a two-sided cusp. So it's going to come along here, and then it's going to go like so, like that, like the seagull shape. And then it goes along and it passes through as a single x-intercept through 27. Okay, and that, folks, is your graph right there. Now, what we would have to do, remember that this original graph actually had a vertical shift of 5. So in fact, what it would look like is this, and then it would pass through right there at 27. It would be up 5, so it would look like that. But again, you're just trying to get a general idea of the shape. Okay, folks, so that's I know those screencasts are long, but there's a lot of really good mathematics in being able to rough sketch these functions. I think it's really, really worthwhile for you to take some time and practice doing it, because it reviews the end behavior and the x-intercept behavior that is so important in functions and in calculus. Okay, so hopefully that helps, and now you should be able to go through and rough sketch the ones that I didn't do.